All right, there we go. A little bit on the calculus here for AP Physics C on momentum and impulse. All right. Did a little bit of background yesterday in terms of the fact that force is the rate of change of momentum, but then also change in momentum then is equal to the integral of force with respect to time. I'm putting the vectors over here. I didn't even talk about the vector notation today in class, but there it is. So I'm going to just jump into number 5 here. You just got to be careful which function you're given and, applying the right technique to it. So number 5, it gives us a force function, 3t squared minus 2t newtons is applied to an object for 6 seconds. Now this is a time-varying force. Time-varying force. These are not something that's super common in nature, right? Time-varying force, a force that is modulated or changes depending on the amount of time that has happened. Perhaps it is a fan, you turn on a fan and it gets up to speed in a certain amount of time, and it was blowing on something, so the force of the air on a little sailboat or something. Could be a boat motor, something like that, where you crank it on, and as the propeller gets up to speed, the force increases. Often forces in nature are position dependent, not time dependent. Meaning they're depending on where something's located. But nonetheless, this is the mechanics of solving these problems. Okay, so sometimes it's hard to put a visual representation or a mental representation on one of these force functions. That's kind of my point. So a force of 3t squared minus 2t newtons is applied to an object for 6 seconds. So what we should realize here is, okay, it's increasing, but the rate at which this force is increasing is going down because of -2. It's leveling off. It'll level off possibly eventually. Determine the object's change in momentum. All right, so number 5. So the force function is 3t squared minus 2t. And I put units on it so you can see that. The length of time is 6 seconds. So what does this function look like? Well, I don't know. It doesn't really matter so much, right? You plot it in your calculator, see what it looks like. Let's just go ahead and rip through the math here. So the change in momentum of this object due to this force acting, let me turn this off. The change in momentum of this object due to this force acting is going to be the integral from 0 to 6 seconds of 3t squared minus 2t with respect to time. Alright, so this would be 3t cubed over 3, take the antiderivative first, minus 2t squared over 2, evaluate from 0 to 6. Alright, got a calculator right over there, so we get 6 cubed minus 6 squared for our change in momentum. Now, fortunately, I don't have one of my students in class here to check my work, which is often something that I benefit from. One of my students can tell me quickly if I made a calculation error. 6 cubed minus 6 squared is 180. So I have a change in momentum of 180. Let's see here, how we're doing. I'll write it below it. 180, and units of momentum this has to be. So there's 2 different units of momentum. This is force times time, so this would be Newton seconds, or kilogram times meter per second. So the change in momentum of this object is 180 newton seconds. Now, we take that change in momentum and answer some questions now. All right? And once you find the change in the momentum using the calculus, the other questions are really, just using basic definition. You found the change in momentum or the impulse here. You did calculus to get that. Now, the beauty here is you can just take that and set it equal to m delta v. You set that equal to m delta v without having to do any more calculus or anything, right? So the next part says, determine the final speed of the object if its mass is 2 kilograms and it is initially moving to the left with a speed of 15 meters per second. So, all right. So I'm going to save this delta p here. Give myself a little more board space. I'm writing fairly large so that hopefully it translates in the video. Trying to speak up as well. All right. So delta p is always equal to m delta v, right? So if it's in this part b here, right, we're going to say it's 2 kilograms and it's moving to the left. The initial is negative 15 meters per second, or v naught, I suppose I should say. So v naught is negative 15 meters per second. Delta p came out positive here. That means it's positive. All right, came out positive here. It's positive. The force, the signs on the force tell us the sign, the direction of the momentum. All right, so we just plug everything in here. We say, okay, positive 180 newton seconds equals 2 kilograms. Now, here's the deal. I haven't talked about this in class. Sometimes I think it's easier just to solve for delta v. Rather than putting in v initial and v final, if you just solve this for delta v, divide both sides by 2, you get a delta v of 90 meters per second. Now, let's see how the units cancel out here. Newton is a kilogram times meter per second squared, right? All right, so kilograms would cancel, one of the seconds would cancel, you get meters per second. So delta v is 90 meters per second. So now, and it's positive. Its velocity is going to change by positive 90 meters per second. So if it's going negative 15 meters per second to start off, and it has to change by positive 90, it's actually going to turn around. All right, so we spend 15 meters per second, positive 15 meters per second to come to rest. Then it's going to have another 75 meters per second to get up to velocity, to get up to the final of positive 75 meters per second. So this ball will get turned around by this force and then shot out. So maybe it's, I don't know, maybe it's something running against a rubber band and then it gets flung backwards. I have no idea. Like I said, the physical reality of this force is difficult to visualize. For part C now, determine the final speed of the object if its mass is 2 kilograms and it's moving to the right with a speed of 15 meters per second. So the nice thing is, I already know that no matter what, no matter how it starts, if this force acts for that amount of time, its change in velocity has to be positive 90 meters per second. So if I start off going against it or going with this force, then the change in velocity still has to be positive 90 meters per second, because the change in momentum equals 180 m delta v. So the initial condition in this case is v naught is positive 15 meters per second, right? Therefore, v final would be positive 105 meters per second, right? It's going to gain that velocity. You can always, to find the final velocity, you can always add the change in velocity to the initial velocity, right? So plus 90, positive 90 plus negative 15, positive 90 plus positive 15. So that's that. Now, Number 6 here is the opposite way of doing this. You start with the momentum function. All right? So if you start with the momentum function, all right, so if you start with the momentum function, then the derivative of the momentum function with respect to time gives you the force function. All right, so then you can evaluate that now at a particular time and figure out the force. So a 1.5 kilogram object moves with a momentum of negative 3t squared plus 6. All right, so the mass of this object is 1.5 kilograms. All right, the momentum function here. And I'm not putting the vector symbol on this right now. I mean, I guess I could, but it doesn't. I probably would have to declare which direction it is in as well. You know, with some hat notation or with a note or something. Or maybe I'd have to say it's the x component of the momentum, whatever. It's just one single dimension. So there is there's a momentum function. So it asks us to determine at what time the object will come to rest. So it's at rest when v equals 0, which is also when the momentum equals 0, right? So 0 equals negative 3t squared plus 6. So 6 equals 3t squared divided by 3 divided by 3. I get t equals radical 2, which is like 1.4 seconds or so when it comes to rest. All right. So it moves with this momentum, right? And it's going to come to a stop in 1.4 seconds if it keeps following this momentum function. Well, that's weird, right? Because then the next question says determine the net force acting on the object at 5 seconds. So it's going to come to rest. And then what? Well, let's think about what this momentum function is telling us. So negative 3t squared plus 6. The initial momentum of this object is 6 kilograms times meters per second. So it has an initial positive momentum. And then this negative 3 tells us that the momentum is going to increase in the negative direction. So it's going to kind of slow down and turn around and go backwards. Interesting thing, you just divide this whole thing by mass. All right? So if you actually just take this function, right? Velocity equals p over m. You can literally take this function and divide it by 1.5. All right? Literally divide each term by 1.5. Divide out the mass, and you have the velocity function. So negative 2.0 t squared plus 6 divided by 1.5 must be 4. All right, so that's actually the velocity function. That's kind of fun, right? But anyway, most people don't think about doing that. The fact that you can divide a function, you think of that whole thing as momentum, divide the whole thing by the mass, and get the velocity function. You know, we usually don't do stuff like that, but it's kind of interesting to think about. So determine the net force acting on the object at 5 seconds. Well, that's not too hard. All we got to do is take the derivative of the momentum function. All right, so force equals dp dt. All right, so the derivative of the momentum function is negative 6.0 t. That term is 0, right? So our momentum function here is negative 6.0 t. So the force at 5 seconds is negative 30 newtons. right? Pretty cool. So the direction of the force, it's going to be always negative. It's always getting pulled backwards. So this is a time-varying force. It's just linear. So it gets more negative as time goes on. This is kind of like a Hooke's law. A spring would act like this, right? If you're attached to a spring and you go forward, right, you're always getting pulled backwards. And the farther time goes on, well, it's not really, I shouldn't say that, right? Because that's position dependent. It's kind of like a spring. As if you keep going in one direction, time goes on, the force is going to increase as the time increases. It's a bad example, really. Anyhow, a constant increasing force with time. I don't have a good example of that in nature. It could be a machine, right? That you flip the switch and slowly it, compresses like a hydraulic press. Just constantly increases with time. But again, usually that's based on position, not time. So that's kind of an interesting one there. So that's how the calculus works. If you have a force function, you can take the integral of it, find the change in momentum. If you have a momentum function, you can take the derivative of it and find the force. And typically evaluate it at a specific time to get the instantaneous force. The last one, 7, I'm going to have you do on your own. I had to give you a force function. It says determine the mass. Now this is the key, right? And this is why we deal with momentum functions, because we can figure out the momentum, for instance, in high energy physics, particle physics, we can figure out the momentum and energy a particle has after it undergoes like a nuclear fission or something, right? We have detectors where the radioactive particle, a proton or electron or something, can hit it, an alpha particle, can hit the detector in a particular location, like in a particle collider, right? The particles hit each other, and there's like a cylindrical detector around it that has many little detectors built into it, almost like a cylindrical screen, pixels. Think of the pixels as being the detector. So they collide; these parts fly off all different directions. Well, when it hits those little detectors, little pixels, we know where it is, right? We know where the collision occurred. We know where the particle hit the cylinder wall. And we know its energy and its momentum. So from the energy momentum, you can calculate the object's mass, which is what we're looking for typically, right? We're typically looking for, in these particle collisions, to find the energy of something and or momentum, because then we can figure out the mass of the particle. And that's how we find these new fundamental particles and stuff in particle colliders. Super colliders, that sort of thing. Very cool stuff. So this is a little more of a real world example in terms of what you would do with a momentum function actually, or a force function. So good stuff. Good stuff. That's about it. Then we're going to move on to some collisions. The collision stuff is, we're going to go through pretty quickly. It's no more complex, at least for now, it's no more complex than what you did last year. We are going to talk a little bit about conservation of the center of mass this year, possibly. That is an important concept. It can help you solve problems. But anyway, for now, that's it. Take it easy.